Okay, let's dive in. Today, we're digging into a really specific bit of meteorology, atmospheric occlusions, using some pretty detailed source material on atmospheric dynamics.
That's right. And our goal really is to get a solid handle on what occlusions actually are. How they form, the different types, because there are different types,
Yeah.
and crucially, the kind of weather they tend to bring.
Yeah, because this isn't just theory, is it? This is about a key part of how major weather systems evolve, the kind that definitely affects, well, everyone listening.
Yeah.
So where do we start? How does an occlusion actually happen?
Okay, so picture your standard frontal depression, right?
Mhm.
You've got a low pressure center with a warm front and a cold front snaking out from it. Well, usually that cold front moves faster.
Right, the cold air is denser, cuts underneath.
Exactly. And an occlusion forms when that faster cold front literally catches up to the warm front ahead of it. It overtakes it, and they merge.
They merge. So what happens physically when they meet?
Well, think about that wedge of warm air that was sitting between them, the warm sector. When the fronts merge, that warm air gets squeezed upwards, lifted completely off the ground.
Ah, so it loses contact with the surface entirely. The warm air is just up there.
Precisely. It's displaced upwards. And there's a specific spot where this whole process is sort of anchored, isn't there? The source mentions it.
Yeah, the point of occlusion, or sometimes called the triple point. That's where the new occluded front meets what's left of the original warm and cold fronts.
That's the one. It's a key feature you'll see marked on weather charts. It shows you where that merger is happening.
Okay, so fundamental mechanism. Cold front catches warm front, warm air gets lifted. But then the source immediately says, hold on, it's not quite that simple. There are different types of occlusions, and it all comes down to temperature.
This is where it gets really interesting and maybe a bit counterintuitive at first. The key thing isn't the temperature of the warm air that got lifted. It's about comparing the temperatures of the two cold air masses involved.
Two cold air masses.
Yeah, the cold air that was ahead of the original warm front and the cold air that was behind the original cold front, their relative temperatures determine everything.
Okay, a battle of the cold air then. Let's take the first type mentioned, the warm occlusion. How do we identify that one?
Right, a warm occlusion happens when the air mass out ahead of where the warm front was is actually colder than the air mass trailing behind the cold front.
Hang on, the air ahead of the warm front is colder, but it's called a warm occlusion. That feels backwards.
I know, it sounds odd, but think about what's happening. The air behind the cold front, even though it's cold, is less cold or warmer, relatively speaking, than the air mass it's running into.
Ah, okay, so less cold meets even colder.
Exactly. So in a warm occlusion, this less cold air behind the original cold front is forced to ride up and over that really cold, dense air that was already sitting there ahead of the warm front. That very cold air stays near the ground.
Got it. The less cold air does the overriding because the air ahead is just too cold and dense to be pushed easily. Where does the source say these tend to form?
Typically, they're more common in winter, especially near coastlines like in Europe or North America.
Mm-hmm.
You often get really cold continental air pulled in ahead of an approaching system, setting up that crucial temperature difference.
And if you're looking at a weather map, what does the line itself look like?
For a warm occlusion, the occluded front symbol, usually that purple line with alternating semicircles and triangles, tends to follow the track where the warm front used to be. The original cold front line kind of fizzles out, or looks broken where it meets the occlusion.
Okay. And the weather associated with it, still pretty impactful, I assume.
Oh yeah, you've still got all that warm air lifted, which means clouds and precipitation. And the clouds from the cold front, often the more vigorous cumuliform types, get sort of pushed up into the broader, flatter stratiform clouds from the warm front.
So like thunderstorms hiding inside steady rain clouds?
Precisely. That's the hazard of embedded cumulonimbus or CBs. Nasty surprise if you're flying through what looks like just layered cloud. And crucially, for a warm occlusion, most of the precipitation tends to fall ahead of where that occlusion line is drawn on the surface map.
Right, because the overriding air is producing the precipitation further forward.
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best